Hello, it is time for the anxiously awaited follow-up to the part 1 of the transistor design tutorial. Yep, it's time for part 2. So we have our breadboard completed, we have the signal generator down here, and the power supply up there. Power supply is set to 10 volts. Signal generator is outputting a 100 millivolt peak-to-peak signal at 1 kilohertz right now. That's going into our breadboard. And it's going into our oscilloscope. It's monitoring both the input signal and the output of our transistor amplifier. So let's move forward and we'll take a look at the breadboard, see what we've got. Okay, so here's our circuit on the breadboard. Sorry, it's sloppy. I kind of threw it together and yeah, it looks really bad. But you know, it works, so no problems at all. Anyhow, we have our input capacitor here, our 0.1 microfarad. So we have this red lead here coming in. That's our signal coming in. Going into the base of the 3904 transistor. We have a bias resistor here and down here. We also have the emitter resistor, the 100 ohm, with a currently 10 microfarad capacitor across that. So plenty big enough to pass all the frequencies. And we have also the collector resistor. I don't think it's that one. It's back here behind the capacitor, hard to see. And then off of our collector we have our output coupling capacitor, again 0.1 microfarad, going to our 1K ohm load where we have our other oscilloscope probe. So we've got one oscilloscope probe here on the input side, just basically showing what the signal generator is giving us. And then we have the other on the output side, which shows what the output of the transistor amplifier is. So, I know what you're thinking. Let's take a look at the oscilloscope and see what kind of signals we get. I apologize if that's at all blurry. I tried to get it as in focus as I could from the distance I was able to achieve. Anyhow, you can see channel 2. Let me get my pointer, talk through this. Hopefully you can still hear me. You can see here channel 2. In blue, that's our input waveform, and you can tell they're scaled the same, channel 2 and channel 3. Channel 2 we have 200 millivolts per division, and channel 3 also 200 millivolts per division. So they're on the same scale. You can see that we have the roughly 10 times amplification there, where here we have our measurements on blue is channel 2, our input, volts peak to peak. It's set to 100 millivolts. It's a little bit off. It's not the best signal generator in the world, and you know, it may not be 100% accurate. And then our output is roughly about 10 times greater than our input. At right now 1.02. It's jumping around a little bit. It's in yellow mode, but yeah, they're both jumping just a little bit. It's not too bad. Anyhow, this was jumping a lot worse, and it turned out that the issue was grounding issues. And if you saw a couple videos back, I talked about the grounding issues in my lab. That's since been solved, and it seems like my oscilloscope, my signal generator are a lot steadier. So go figure. Apparently those need to be well grounded. I guess it's kind of obvious, but you know, I've talked about people, or I've heard about people rather, that have taken their oscilloscope and they want to do isolated measurements. Let's say that, well, as you may know, because the ground side of any one of these channels on the oscilloscope is mains earth reference. That's why they have these nice plastic protectors around it, so you don't touch it. Because it's mains earth referenced, a lot of people will plug the mains power cord of their oscilloscope into an isolation transformer, which will let them measure mains voltage directly. That's not generally a good idea, and as I found, it can actually be problematic because you don't have a good actual earth ground on the oscilloscope. On this particular model, the Rigel DS1054Z, that does apparently make a difference. Anyhow, so I wanted to show you what we're getting. Obviously our amplifier is working quite well. It's working as designed. We got our times 10 gain that we calculated. There's a little bit of a difference. It's not exactly times 10. But there's reasons for that, and not only is Do you have variations on the input signal, which clearly isn't exactly 100 millivolts peak to peak? We had rounded on our bias resistors. Remember that originally we had a resistor that was supposed to be close to 13K, and I ended up going down to 12K because it turned out that I just didn't have the resistor that I needed. So that did affect our bias slightly, which will affect the distortion on this sine wave. Now it looks pretty clean, but if you were to put that on a distortion analyzer, you'd probably find that there's slightly more distortion because that bias isn't perfect. And then the main reason that we're going to have differences in our actual amplification value has a lot more to do with the emitter and collector resistors. And of course, even if you had that perfect value that we calculated, it wouldn't actually come out to be the perfect gain that you were expecting, because resistors have tolerances. So let's say that we had a 2090 ohm resistor with a 5% tolerance. You're still looking at plus or minus 5% of 2090, whatever that is. Let me calculate that. I'm curious now. 2090 times 1.05. So you could be as high as nearly 2200 ohms, or as low as times 0.95, as low as 1985 ohms, give or take. So you can see that there would be huge differences there from what we had actually calculated. Now you could get 0.1% resistors. They make 0.5% resistors that are also pretty reasonable. I'll show you really quick. I can grab it here. I also have this resistor box here that I had built, and this is a 0.005% tolerance resistor. Very, very accurate. In fact, I actually tweeted a photo, if you follow me on Twitter, of measuring this resistor, where I was actually measuring out perfect zeros all the way down to a 1/10 of an ohm. So really accurate resistor, really good temperature coefficient, and I use that kind of as my resistance standard in the lab. $20 resistor, something like that, if you can believe it. Resistors get even more expensive than that, especially as you start getting towards the high-end values of resistance. I found on Mauser the other day a 1 tera ohm resistor. I can't even imagine what's involved in trying to use that. I have somewhere here in the lab, maybe I'll take a picture of it, put it on Twitter, a 1 gig ohm resistor. That's the biggest I have here in the lab. Even that comes with a pair of gloves, rubber gloves, that you have to put on. I guess it's not rubber, it's latex is rubber, I suppose. I'm not sure if they're latex or what, but you get it, like a surgical glove that you hold it with, because even the oils from your fingers will allow enough current to go around that resistor and disrupt your resistance reading at 1 gig ohm. And of course, if you're using low voltage, the amount of current that you're running through that resistor is tiny. You're talking nanoamps or maybe picoamps. So you definitely need to keep that in mind as well. Signal integrity really becomes an issue. Anyway, I've completely digressed from what we were talking about. But so anyway, resistor tolerance is probably a huge part of why there's variance there. And again, we did a cookbook method. You're assuming that the beta of this transistor is exactly 180. Well, that's not necessarily the case. It varies with temperature. It varies with manufacturing tolerances. So we got pretty lucky here in that our gain is relatively close. Let's calculate that quick and see what gain we actually got here. So we have an input, let's just say 112 millivolts, and an output of, it's jumping around, let's call it 1.03. It's kind of in the middle of where it's jumping. So what you do to do that, you take your 1.03 divided by 0.112, which is your input. So gain is the output divided by the input voltage. And what do we get? We get 9.2 for our voltage gain. So yeah, that's relatively close to the 10 that we would expect to get. I'm pretty happy with that. So I know you're wondering what happens if we start dialing up the amplitude to this amplifier. What happens when you get to an output signal that's so large that it's actually starting to hit the VCC rail and your ground rail of your power supply? Well, let's try it. Right now we're at 100 millivolts peak to peak. Let's go up to 200 millivolts. Obviously we're off the scale, so let's adjust that. There we go. So now we're looking at 200 millivolts peak to peak in, 2 volts out, roughly. Aha! Do you see there? There's a little bit of distortion in this waveform right here. You see it's on every repeating edge. There's a little bit there, but mostly it's noticeable right there. And you notice that this peak is a little bit sharper than this peak here, where it's a little bit more rounded. That's at just at 2. But watch what happens when I go over to 300 millivolts peak to peak input. Now it gets much more pronounced. And you notice that that's much sharper. Let's keep going. Why not? What can we hurt, right? Just a transistor, it's a 10-cent part. That point's getting sharper, and again you're seeing that curve, that little kink right in the middle of the waveform right there. Let's keep going. There's 500, 600, 700. Let me get that back into. See, we're only getting about 5.4 volts peak to peak out of this. And that's not really surprising because, like I said before, you're not really going to get rail to rail. You're not going to go all the way down to ground. You're not going to get all the way up to your 10 volts. If we were to cascade and do a 2-stage amplifier, you would be able to amplify the first stage rather cleanly, and then your second stage you'd probably get enough gain to saturate that and clip and see your top and bottom rails. Maybe I'll do that. Maybe I'll design and add a second stage to this, and you can see. And ultimately, we could turn this into essentially a square wave. But we're getting to a point where I'm not sure how much further we can go. Let me get this back in frame again. Oops, wrong way. Look at that. Aha. 9.6. See, like I said, we're not going to really hit that top and bottom rail, and in fact, we can keep increasing our input as much as we want, but we're really not getting a whole lot more out. See, it says 12 volts, but part of what you're getting there is bleed through of the actual signal, which is adding to that, because remember, there's a diode, there's capacitance, and it's acting a bit as a voltage multiplier. So that's it right there. Look at that distortion. I'll take this other one off. Turn that off. Oops. You can see that a little bit better. Yeah, that's interesting. So that's what happens when you put a signal that's vastly too large into a single stage amplifier. You get that kind of distortion. So, probably another question you're thinking of, and I don't blame you. Can we blow this thing up by adding too much voltage to it? Well, yeah, eventually we'd get to a voltage where you could blow this thing up. But it typically takes about 30 volts from collector to emitter, and this is a 30 volt power supply. But let's try it anyway, and I think it'll be really interesting to see how our waveform, which is, remember, I've got it pretty much full clip coming into this thing. Let's see how that distortion starts to occur. Coming up now, I'm at about 5 volts. There's the 10 we were at. 15, 20, 25, and 30. It just basically disappears again. So I'm going through from 0 to 30. Really interesting how that distortion changes. Kind of trippy, isn't it? I like it. Anyhow, obviously we're not able to blow this thing up, but yeah, it's really interesting. And the reason that you see that clipping and the distortion of this waveform change is because as you change your supply voltage, you're changing the bias point as well. Because remember, our bias calculation had to do with our supply voltage. So what you're seeing is it's saturating and going between saturation and cutoff at different points in time as the bias changes. Anyhow, thought that would be interesting. I don't know about you, but I wasn't all that impressed or enamored with the results that we got on the oscilloscope. It's nice to be able to see the waveform and see what it's doing, but I want to hear what it sounds like. I want to get a feeling for what it sounds like. It's not interesting enough just to know what it's doing. So I got this old piece of test equipment out here. Let me show you it closer. If you've come to the conclusion that this thing is ancient, well, you're right. It's from, I'd say, at least early 60s to possibly early 70s, but this does have a vacuum tube inside it. So it could be as late as maybe late 50s to mid to late 60s, most likely. It's a Heathkit. It's a model IT12. What does it do? Well, it says at the top, signal tracer. What it does is you have a probe, which is here, and you can see it says audio and toward the left and RF to the right. What it does is it's meant to be used with radios primarily, where it has a detector built into it, so you can use it with radio frequencies, and you can probe through the radio and see where any issues might be occurring. But you can also use it for audio circuits. And the nice thing is it has a built-in speaker here, and you have a level control on off. You can turn the speaker on or off. This is a switch for noise immunity on the bottom, but it doesn't really make much of a difference. And down here you have what they called back in the day a magic eye vacuum tube. It would actually open or close based on your signal strength. So let me go ahead and turn the power supply up, and we'll listen to what 400 Hertz sounds like as we go through and distort that waveform between 0 and 30 volts like we had done before. It's relatively quiet. Let me turn it up here. There we go. Kind of weird sounding. Let me turn up the amplitude. It's kind of like a weird space sound or something. And you can see, let's see if I can zoom in on it, our magic eye tube down here. Focus that the best I can. You can see right now that's kind of open. You see it's at like maybe a 30-degree angle toward the bottom where you see a darker part. Let me go through and change our voltage, and you should see it kind of opens and closes there. Especially there, you can see that. Okay, while that was interesting, using the signal tracer, I feel like we can do better, don't you? So here I have a guitar amplifier that I actually designed and built. It's my own design. And it's a vacuum tube guitar amplifier. Let me show you the back and I'll discuss the design a little bit further. Okay, sorry, it's going to be blurry and shaky. I had to go handheld here to get the shots that I wanted. Here's the back of the amplifier. Now this is a 5-watt single-ended output amplifier, so it's not real super loud. It's good for like practice level. And you can see here we have the rectifier tube for the power supply. And then back down up in there we have, if I can point, two 12AX7s there. These actually happen to be ECC83s. That's the British version of the tube, but they are essentially the same thing. And we have a 6V6 output tube right here. And back behind there, you might be able to see the output transformer. It's a massive thing from Mercury Magnetics. You can see back in there some more of the power supply stuff. And that is a 10-inch Alnico magnet speaker. So let's try this bad boy out and see how it sounds through our makeshift little solid state amplifier. Probably terrible, but hey, let's give it a shot. Okay, so I have my guitar connected up to the amplifier just directly for now. I've got my Gibson Les Paul Studio in mahogany. It's a bit dusty, that's embarrassing, but for those of you that followed my video feed and saw my interview advice, I did actually get the position, so I'll be working a bit more, but hopefully that doesn't interrupt my flow of videos. I'm certainly going to try to keep them up. Anyway, wanted to show you what the guitar sounded like, just clean through the amplifier before we muddy the waters with my crummy single transistor amplifier. My ring got caught in there. I should take my ring off when I try to do that. Okay, we have something very strange happening, and I'm going to put the camera right up next to the speaker and see if you can hear that. You hear that? That's a radio station being received. I'm not sure if you can actually hear that or not through the camera. I hope you can. Strangely enough, a radio station is being received. I just hooked it up through our transistor amplifier. Clearly what's happening is some of these long alligator leads that I have there are acting as an antenna, and the transistor acts as a detector, and there's capacitance there which actually demodulates the signal along with the diode detector and the transistor, and we are able to receive radio stations. And if I let go of the guitar, it makes a lot of noise because we have some grounding issues. There's probably a ground loop here, but yeah, so there's some strange things going on. But let's hear how this amp, that's now cranked up to the max, let's hear what it sounds like. You can actually hear it over the radio station. It did get a lot louder. It doesn't necessarily sound better. It doesn't necessarily sound worse, I don't think. It's certainly a lot more treble. It's not getting the bass through that the amplifier by itself gets. It sounds very tinny. Certainly it doesn't make it sound warm and rich like the tubes do. I think that's kind of a symptom of going through the transistors in general. That's why you have the tube purists that don't like transistors or any type of semiconductors in the signal path. I just don't like the way it sounds. But certainly there's people that like vacuum tube guitar amplifiers that are a little bit more chimey and trebly. Look at Vox. You know, people like Vox amplifiers. I think those don't have quite the warm tone. Who says rock is dead? Well, okay, maybe not a big improvement over where it was. Actually, no improvement, I'd say, but it was interesting nonetheless. Anyway, I hope you found that interesting. Able to design our own amplifier from scratch, play with it a couple different ways to test it and see what kind of results we got. And, well, maybe not the best for a guitar amplifier. I think it's not going to be the biggest new music craze sweeping the country, but I think if we added a second stage to that, we could get some really interesting fuzz sounds, and we might do that later, except we might use vintage transistors. I might even call them antique because they're from the 1950s. Not sure how the whole grading scale goes for that, but yeah, maybe look forward to that in future episodes. Anyhow, again, hope you found that interesting. Click like if you liked the video. Click subscribe if you haven't done so, and follow me on Twitter at OhmsAtHome. Thanks.